The next speaker is Professor Ling-Yan Hung from Tsinghua University. The title is the CFT Factory, critical lattice models from competing onion condensation in symTO. Let's welcome.
So I would like to thank the organizers for giving me an opportunity to speak here. So today what I'm going to talk about is a systematic way of constructing critical lattice models such that in the thermodynamic limit it has possibility of high likelihood flowing to a continuous field theory, to a conformal field theory. And this is a series of work that started back in 2019, and it was inspired by some observations made in the condensed matter community. This is some work done with my students and postdocs over the years, and also with my longtime collaborator, Eden and Zhao, and also now my student, Shen Ce, now my very trusted collaborator. So let me motivate a little bit why these kind of problems are interesting. Why are we interested in critical lattice models in the first place? So statistical lattice models, they are by themselves an important area of studies, both as an area in mathematics and but also in physics. There are lots of important mathematical structures that have been discovered in these statistical model, and there are important physical phenomena, particularly about physics of phase transitions that we can understand through studying this statistical model. But the statistical model play a particularly important role when it comes to understanding field theory. Historically, lots of interesting, the most important classes of continuous field, conformal field theory were in fact discovered in the thermodynamic continuous limit of lattice models when they are undergoing, when the coupling of these lattice models are tuned to criticality and the model is undergoing second order phase transition, continuous phase transitions. And so the study of continuous phase transitions in statistical model is allowed people since the early 20s, the Ising model, all to discover actually very interesting, important classes of examples of conformal field theories, particularly in 2 dimensions. And in fact, not only the Ising model, the entire A-series minimal models were first discovered from the point of view of statistical models, and there were large classes of integrable lattice models that gave us lots of insights of non-perturbative interacting field theory. So that is so the lattice model not only allows us to inspire us with new conformal field theories, it also provides a UV complete non-interacting description of the field theory. And that is itself very hard to achieve if you start directly from a field theoretic description. As it is well known, we have difficulty dealing with strongly interacting field theory, even in 2 dimensions in general. Even with the help of Virasoro symmetry, it is very difficult to construct new CFTs beyond minimal models. But that is not rational, for example. And so this is just to motivate how important it is to study critical lattice models undergoing second order phase transition. But there's also a question: how do you construct these models in the first place? What are the for some time now, it seems that it is quite difficult to construct new models that is exactly tuned to criticality. So if we don't have a systematic way of doing that, then it seems that it is very hard to study field theory systematically, directly from the point of view of this critical lattice model. And with the help of a new generalized version of symmetries, we now have new handles of creating these lattice model, and this is going to be the crux of what I'm going to talk about in the following. So in my talk, I'll first describe what is the topological holographic principle that is going to play a central role in our construction, and then I would describe the observations that were made in the condensed metal literature called the strange correlators. And based on these observations, we figured out the basic pattern that goes behind these observations, making use of the mathematics of tensor categories. And that allows us to, first of all, reconstruct all these models, all these examples that were observed before, and then to generalize it to new examples. And we will show that indeed we can reconstruct critical points, and beyond critical points, we can even construct phase boundaries, phase diagrams based on the structure that is encoded in the tensor categories. And finally, we discover a couple of new critical models that carries the so-called Haagerup symmetries, and then we'll summarize. So what are generalized symmetries? The idea of generalized symmetry is that instead of usually when we talk about symmetries, we are usually focused on group symmetries, group actions, such as Z2 reflection actions, and so on. But generically, later it is realized, perhaps in the past 10, 15 years, that rather than looking at focusing on the group action, we can also focus on the conserved quantities in the symmetry. And in the conserved quantity, you can think of the conserved quantity as a topological operator, because when I want to count a number of charges, electric charges, I look at the charge operator. The precise shape of the charge operator, a codimension 1 operator, is not important. As long as it encodes certain charges in the system, it would give me the same expectation value. And therefore, generic conserved quantities, you can think of them as topological operators. And so so instead of looking at the precise group action, we ask what is the symmetry, what is the mathematical structure that is formed by these conserved quantities. And it turns out that the mathematical structure that governs these conserved quantities is the so-called fusion tensor categories. And if I look at the collection of these operators, then they form generically a fusion tensor category. And if these operators consist of codimension 1 operator, codimension operator, codimension 3 operators, and so on, operators of different dimensions, then the collection of all of these objects would basically form the mathematical structure is governed by a so-called higher fusion tensor category. And in this talk, we will be focused on constructing two-dimensional models, or 1+1 dimensional models. And so all we need are codimension 1 operators, line operators, and they will form a fusion tensor category in this case. And so then, after people realize that the idea of symmetries can be effectively generalized, there comes this so-called topological holographic principle. This is a very useful observation or physical theorem. I don't know to what extent it can be proven in general rigorously, but so far there has been a huge class of important examples that has shown up. And so basically the topological holographic principle states that if I have a quantum field theory, a system in d dimensions, and it has certain symmetries that are described by a fusion tensor category, then the path integral of this d-dimensional system, or the partition function of this d-dimensional system, can be expressed as a path integral in a d+1 dimensional topological field theory. This TQFT is constructed using the data of the fusion tensor category that governs the symmetry of the d-dimensional system. And I do the path integral over a d+1 dimensional manifold, do the path integral of the d+1 dimensional TQFT, and I choose a d+1 dimensional manifold that has the shape of a sandwich. So that is shown here. And on this d+1 dimensional manifold, on one side of it, I have the one side of the boundary, it is a d-dimensional boundary. I have to put in some non-trivial boundary condition that controls the dynamics of the d-dimensional system. And then on the other side of the boundary, it is some topological boundary conditions that is completely that has a finite number of choices based on the topological, the TQFT in the bulk, and a general statement is that an arbitrary d-dimensional system that is that has a certain symmetries can always be formulated in terms of this sandwich using a d+1 dimensional TQFT. Then the crucial question is the following. The crucial question is why do we want to express it in this form? In principle, it doesn't carry more information. The extra dimension in the TQFT basically just imposes brute force. It imposes brute force the symmetries that is carried by the d-dimensional system, making the symmetries explicit. That's all. But then it actually converts the problem of looking for this d-dimensional symmetric system by turning it into a problem of classifying non-trivial boundary conditions of these topological theories. So we have converted this problem of looking for symmetric systems in d dimensions into one of looking for non-trivial boundary conditions of a d+1 dimensional topological field theory. And that leads to certain simplification that is very important in the current study. So what I'm talking about here is just some basic principle. But then in the rest of my talk, I'm going to talk about precise lattice models. And that lattice model is a realization of this sandwich picture. And this realization is the so-called strange correlator that was initiated by observations in the condensed matter literature. Okay, so the integrable. So what is this observation in the condensed matter literature? So this observation goes back to about 2006, but then there were new versions of it coming out later in 2016 and 17 and so on. So it has been around for some time. And the observation was very mysterious. The observation is there is a large class of lattice integrable models that were already known in the literature for a very long time, the RSOS models, Ising spin models, there are lots of them. And it was just observed, and these models are two-dimensional models defined on a graph on the plane, on a two-dimensional surface. And it was observed that it is possible to look for boundary, so to look at the ground state wave function of a three-dimensional TQFT, which is, and this three-dimensional TQFT is the so-called Turaya-Viro TQFT, or also known as the Levin-Wan model in the condensed matter literature discovered the Hamiltonian formulation essentially. So there's a TQFT in 2+1 dimension, called Levin-Wan model or the Turaya-Viro model. So the observation is now look for the ground state wave function of this TQFT. Wave function is defined on the codimension 1 surface of this 3D theory. So this wave function is defined on a two-dimensional surface. Okay, and now I am indeed trying to model a two-dimensional lattice integrable model. So what do? The observation is that I pick another state that is also defined on this two-dimensional graph. So, but let me explain a little bit what the wave function of the Levin-Wan model looks like. So the Levin-Wan model on a two-dimensional surface, to define the lattice model, I have to first triangulate the two-dimensional surface into triangles, okay? And then on each edge of the triangle, they are colored by the Hilbert space that is spanned on each edge is basically by the objects of the fusion tensor category of that defines these models. So in the fusion tensor category, the basic input data is basically a list of labels. And so in the Turaya-Viro model, if I want to look at the ground state wave function, I triangulate this two-dimensional surface, and at each edge there is a collection of labels that I can put on it. So for example, the Ising category has 3 objects, 1 sigma psi. Then on this graph, every single edge can take a value either 1 or sigma psi. So the full Hilbert space would be a tensor product of all the edges of 3 dimensions over this 2-dimensional graph. As a topological theory, the triangulation is not important, as we're going to see, but you can always pick one particular triangulation that the lattice model is going to live on. Okay, and on this triangulation, I can construct the wave function of the TQFT that lives on this triangulation. So there are standard methods of constructing this wave function based on the so-called 6J symbols that define these models. The detail is not important for now. All you need to know is that this wave function can be constructed using these 6J symbols that takes schematically this form. And now the observation is I can pick a tensor product state that colors this surface, this triangular surface. Namely, I can I can project this edge to a specific linear combination of objects in the tensor category. I make a very specific projection. So for example, if I'm interested in reproducing the Ising spin model, what I'm going to do is that first of all, I triangulate the surface into this particular form, and then I insist that this red edges is and the tensor category that defines the Levin-Webb model concern is the so-called Ising category, so that each edge here can take value either 0, 1, or 1/2. There are 3 objects, which is corresponding to this 1 sigma psi. Objects, so they are just different labels of the same thing, but let us call that 0, 1, 1/2 here. And to recover the Ising spin model, it was shown by these people that I want to project these red edges to a linear combination of 0 and 1, and then the green edges, I'm going to project it to 1/2. Okay, and it was just an observation. You can check explicitly that this projection of the wave function of the Levin-Webb model on this graph reproduces exactly the Ising spin model. And it was shown that you can do many other lattice integrable models. You have to choose the Levin-Webb model, the category that defines the Levin-Webb model judiciously. The category that goes into defining the Levin-Webb model depends on the symmetry of the lattice integrable model. It is encoding the symmetry as we described in the previous slide, the sandwich construction of the topological holographic principle. But then it has always been a mystery where these boundary conditions come from. I asked the authors of these papers how did they got these boundary conditions, and the answer I got was that they look at old books, Baxter's book, with all this list of lattice integrable models, and they just realized that for every one of them that comes up, they seem to be always able to find an appropriate Levin-Webb model with appropriate direct product projection of the graph so that it reproduced the lattice integrable model exactly. But then why should these things take these values seems to remain a mystery. And this construction of lattice integrable model is the so-called strange correlator. Strange correlator in the sense that you can understand it as the overlap of the ground state wave function of a TQFT with some mysterious tensor product state projection on this graph, and they are called the strange they are often called the strange correlators. And so for me, I was when I went to this talk, and I was very curious about what these numbers meant. And for the so these are the A-series lattice integrable models. People have found the lattice the A-series integrable models. People have also found the corresponding boundary conditions. All of the AK series model, they all have these 3 objects as a subset of objects, and people find that you can just do the same projection, except recall that we're interested in phase transition point, right? If we're interested in phase transition point, then we can ask at what value of this R does it correspond to second order phase transition of the Ising model of this A-series model. And people have found the critical temperature of the Ising model is known, and you can translate it to these boundary conditions. So at phase transition, these couplings take very specific values. In the Ising model, it is this value, and in the case of the A series model, it is this value. This is the critical temperature, the critical coupling of the lattice model, and it has always been, and people have been very curious. What is so special about these numbers? How did they? How can we understand these numbers? And so for a very long time, I was just pondering about this question without much progress. And in the next couple of years, what I did is that if I cannot understand this value that governs the critical coupling, and I'm only interested in continuous field theory, perhaps I don't need to worry so much about the lattice model itself. I can consider coarse graining the lattice and try to flow these boundary conditions. So what we did in the next couple of years, because we did not have a good idea of how to understand those numbers, we made use of the fact that these topological wave functions, they are topological, and therefore different graphs are related very simply by transformation, by these topological moves that is completely fixed by the fusion tensor category. And so you can imagine replacing the graph by a more coarse-grained graph. So these are lattice constant, the size of the lattice spacing. I can start with a lattice, and then I can replace it by a more coarse-grained lattice, and the transformation between this wave function and that wave function is completely fixed in the TQFT. And now, if I started off with a particular boundary condition, such as the one that is described here, I can imagine that now I replace this part by this. And this wave, this U, this matrix here is completely fixed by the TQFT. I can absorb it to the boundary. And so even whatever boundary conditions that I started with here, it seems to not matter, because it would start to flow under this under this coarse graining. And so if I'm interested in CFT, maybe I don't have to worry so much about the initial values. I just need to ask, what is the endpoint of this flow as I recursively coarse grain the wave function, replace it by more and more coarse grained wave function. And so in 2022, in fact, we published an exact eigenstate of the exact fixed point of this RG operator. And so alternatively, it tells us that when you find an exact eigenstate, that is in fact an exact representation of a continuous field theory. Because if you find an exact eigenstate of this operator, it means that you find the endpoint of the thermodynamic limit, the endpoint of the renormalization group flow. And when you find the exact endpoint, you realize that we realize that this is alternatively a discrete formulation, an exact discrete formulation of a continuous field theory, to formulate a continuous field theory as if it is a state sum model. So it seems that that is, we show that that is possible. We spent a couple of years trying to find this exact eigenstate. But then every time I gave a talk about this, I get questions. And question is, in order to construct an exact eigenstate, we made use of conformal blocks. And if you use conformal blocks to construct an exact eigenstate, then you already know a lot about this continuous field theory that is the endpoint of this criticality, the endpoint of this thermodynamic limit, the endpoint of the RG flow. And so then we seem to not be able to predict new CFTs from nowhere. And so it sounds like maybe we should go back to this problem and actually understand these critical values from the very beginning. And if we can understand this number properly, then we can actually construct new critical models that were not known before. So we went back to the drawing board and tried to and continue to stare at this picture. And very recently, in the last year or so, we finally have an idea what's going on to these numbers. And once we understood how this number was constructed in this original example, then we can generalize. Okay, so what exactly goes into those numbers? So directly staring at the critical value, we didn't see anything. And so we take limits of those couplings. What happens is there some well-known physics when you take limits of this coupling R? And it turns out that there are. In the Ising model, it is well known that when the temperature is very high, that is spontaneous. When the temperature is very low, it is the so-called low temperature limit. All the spins are aligned. There is some kind of spontaneous symmetry breaking. And that is a very well-known topological phase in 1 + 1 dimensions with a gapped phase. And then on the other end of the spectrum, if you take R to be, the temperature that is related to this coupling R, so the usual temperature of the Ising model, if I take beta to be infinity, R approaches 0. So beta to infinity is the so-called low temperature limit. And on the other hand, you can take the high temperature limit where beta approaches 0 and R approaches 1. And this other limit is also a very famous spontaneous symmetry breaking limit of the Ising model, but it doesn't break the Z2 symmetry of the Ising model. It breaks the so-called dual Z2 symmetry. Nonetheless, without going into the details of what this dual symmetry is, these are well-known topological phases that are endpoints, two different extremes of the Ising model. And in the two endpoints of the Ising model, we look at what happens to these red edges. So in the low temperature limit, record that R is approaching 0. It means that all the red edges are projected simply to 0. Okay, and in the other limit where R is when temperature is very low, R approaches 1. So all the red edges in this limit becomes an equal democratic summation of 0 and 1. So we ask, what are these two endpoints? Is there a mathematical meaning to these two endpoints? And it turns out there are. And there is a very understood mathematical meaning to these two endpoints of the Ising model. When temperature is very, very low and all the red edges are projected to 0, this turns out to be a Frobenius algebra in the fusion tensor category. And a Frobenius algebra is an algebra object. So an algebra object in a tensor category roughly means the following. A is a collection of labels within the tensor category. So in the case of the in this special case of A0 = 0, I just pick 0 as the collection that goes inside this algebra. And to define a Frobenius algebra, I need to define a product that can be expressed in terms of linear combinations of fusion channels of this tensor category. So to define an algebra in the tensor category corresponds to solving these numbers, and these numbers F here have to satisfy some algebraic constraints, namely that this product is exactly associative, and then this condition is that it is a so-called a separable algebra. So these constraints are enough to allow you to solve for these values of F. And so Frobenius algebra is something that can be solved as soon as you solve for the as long as you're given the fusion tensor category. Okay, so we observe that in the limit that R goes to 0 and R goes to 1, it corresponds precisely to two kinds of Frobenius algebra that lives on these red edges. Then what about these green edges? What are they doing there? It turns out that these green edges also has a mathematical meaning. These green edges corresponds to so-called modules of the, let me see. Right, it's here. These green edges corresponds to so-called modules of the Frobenius algebra. These modules are precisely representations. They are also a collection of objects in the tensor category, and the module has to have the algebra has to have an action on the module, and it is also expressed in terms of a linear combination of fusion channels in the fusion tensor category. And so to solve for a module means to solve for these numbers, the action of the algebra on the module. And these numbers have to satisfy the fact that if I act 2A on M, it has to be equal to multiplying the A together and then acting A on M. So these rows here can be solved in terms of these F's defined in the Frobenius algebra. Okay, so this is just some, so you can see that this is really the usual definition of representation of an algebra. Okay, And what we observe is that what happens to the original collection of model is that these green edges should be understood as modules of a shared module of two Frobenius algebra that are at the endpoints of the couplings of the temperature. Then you ask yourself, what does it mean? What exactly happened at the critical temperature of the Ising spin model? You realize that these endpoints are two topological phases. They correspond to the so-called gapped phases, and physically, there's actually these gapped phases corresponds to the so-called anyon condensation at the boundary. Anyon condensation is a form of spontaneous symmetry breaking. What happens is that, recall that we have a topological, three-dimensional topological bulk theory, and that bulk theory, there are lots of topological lines. And at these endpoints, some of these topological lines are allowed to escape from the boundary. This is a so-called anyon condensation. And these two Frobenius algebra describe two different ways that these anyon lines can escape from the boundary. But then the anyon lines that escape from the boundary, these two different ways of allowing anyon lines to escape at the boundary, they're incompatible. Some of the things here and some of the things here that can escape do not commute. And so what happens at the critical point is that these two things, both of them are trying to condense, two kinds of different anyon lines are trying to condense at the boundary. And at the critical point, and they're competing, they're not mutually exclusive, they cannot condense at the same time. And at the critical temperature, what happens is that the competition reaches a commensurate state. Nobody wins over the other, and this is where criticality comes from. So understanding this physics gives us an idea of how to construct that critical temperature directly from the mathematics of Frobenius algebra and modules. And so what we did is the following. So what we thought is a natural thing is to do is the following. We divided the lattice into unit cells. You can see that this lattice that constructed the A-series model, the Ising spin model, is composed of these unit cells that involves, so this is a dual graph of the triangulation, of something that looks like a 4-point diagram. And as we described, these slanted edges corresponds to modules. These straight and these vertical and horizontal edges corresponds to algebras. And now, suppose we want to have one set of topological boundary conditions that is winning. That topological boundary condition would correspond to painting the middle edge by the algebra, which is what we described before. And if we express it in completely generic form, so previously at r equals 0, this edge is just projected to the 0 object. But in fact, you can always, what that 0 object between these two green edges, you can in fact express into this form. So in that case, it just corresponds to the fact that x and y take this so-called 1/2 and a is 0. Okay. So, but then you can always express it generically in this following form. And so we have two competing algebra. So what it means is that we prepare two kinds of states. One with algebra A0 expressed in this form, and another state prepared as A1. Okay. And now I want to normalize this state because I want to compare the amount of condensate within this unit cell. And so I have to normalize this state. And to normalize this state, I use the concept of trace in a tensor category that basically corresponds to taking the graph and its conjugate and then connecting the graph. And so this gives us a norm of each of these states in the unit cell. And so this can be computed using the data of the Frobenius algebra. So once I have defined the norm, now I'm able to compare the relative size of these two condensates. And I claim that the critical point should be the value should be at a value when two normalized condensates are exactly are exactly equal. So what I mean is the following. First of all, recall that for given topological phase, I normalize it with this norm that I have just defined in the previous slide. Now, because I'm allowing two kinds of condensates to compete, so I'm just adding them up. And if I've only got one of them, that is one topological phase. If I only have the other, is the other condensed phase. And now, if I have these two normalized phase added with equal weight, then no one should win over the other in the sense of under the thermodynamic limit in the RG sense. And so this should give me the critical temperature if I understand the physics correctly. And in fact, it does. Basically, all of these numbers that people found before that give you the critical temperature of lattice integrable models are completely reproduced by this picture, by this simple set of arguments. Okay, so the idea, so what we have learned is that the module. So what we have learned is that essentially the strategy is to divide the lattice into unit cells. The module is separating the unit cell into these small compartments, and in each small compartment, we try to pour in this condensate that is normalized. Whenever two normalized condensates have equal weight, then that is a critical point where nobody is winning over the other. And so we basically, this module protects these unit cells from having its equilibrium being influenced by the other unit cells. The module basically plays this role. And so, first of all, we reproduce the entire A series using this method, the entire A series critical models using by basically applying. By basically applying this formula, we reproduce the entire n-state pulse model, arbitrary n, based on this formula. And each of them corresponds to a critical point, a phase transition point between these topological phase. Each of this Frobenius algebra gives you a phase transition. And so another important thing is, how do we know it is a second order phase transition rather than a first order phase transition? The idea of a first order phase transition is that is basically a matter of degeneracies. Within this unit cell, you can count the number of edges to count the number of degrees of freedom residing in the red edges. So in the case of this Ising model, these red edges can be either 0 or 1, so it is two-dimensional. And you also count the number of gapped phases or number of Frobenius algebra that can live on these red edges. In the case of the Ising model, there are exactly two such gapped phases, the A0 Frobenius algebra and the A1 Frobenius algebra. So there are two gapped phases and only one relative coupling. The overall normalization is not important, so the only coupling that you only have one coupling to dial within each unit cell. So what that tells you is that whenever you are moving this coupling, you're only moving between this gapped phase. There is not any degree of freedom within this small world of the unit cell to describe degeneracy. But without degeneracy, it is not possible to have a first order phase transition. The idea being that if you are having a first order phase transition, like in the case of water turning into ice, at the critical point, you have to have a direction, have to have a coupling to describe supercooled fluid, and you also have another coupling to describe superheated solid. Because so that at the critical point, these two phases are distinguishable. But since in this small world, in this unit cell, there is no such coupling. You only have one coupling and two phases. Therefore, there is no room for our first order phase transition, no room for this degeneracy. And what happened is that we give us, and so using this counting, we basically give sufficient condition for a second order phase transition in this lattice model. You count the number of edges, roughly speaking, you count the number of couplings that you have. You count the number of gapped phases that you are allowed to put into this unit cell. And if the number of gapped phases is more than the number of couplings that you have, then you basically always has a second order phase transition. And basically, you can test it in an infinite number. We have tested in an infinite classes of models, and so far we haven't found a single counterexample. Now, okay, so we have figured out how to construct these models. Can we construct also phase diagrams? Previously, what we described is constructing only the critical point. If you have two things competing, then the two things, when two things are normalized and commensurate, you get a phase transition point. Is it possible to have more things competing and trace out phase diagram of several phases competing with each other, the phase diagram of this object? And it turns out it is possible. So we first work with an example that is known. It is related to this famous so-called Ashkin-Teller model that was proposed studied intensively in the 50s, 60s. And we find that, and it is known that you can embed these models in a tensor category. And in this case, it is embedded in this so-called A5 tensor category. And now we are going to play the same trick. On each unit cell, the slanted edges, we pick a module. We pick a module that is given by a particular object, m equals 1. We pick a particular module, m equals 1, and there are 3 gapped phases sharing this one module. And it turns out that in this case, you get, the number of couplings is only 2, and the number of gap phases is 3 algebras sharing this module. And it turns out that all of the phase transition points are second order by the counting that we described before. And now, so the phase diagram looks like the following. So I have these endpoints, the gapped phases described by Frobenius algebra. And I can first look at two commensurate points. So A0, A2 commensurate point is located precisely at this point. The formula that I gave gives you precisely this point. A2 and A3 commensurate point give you this point. A3 and A0 give you something here, give you this point. So indeed, all of them corresponds to well-known critical points. Then you ask yourself, how do I trace out these phase boundaries? And it turns out that to trace out these phase boundaries, what you're doing physically is to have the commensurate point between A0 and A2, but then you pour in some more A3 without changing the relative balance between A0 and A2. That should give you this line here. And indeed, we find an analytical expression that is defined completely based on the fusion tensor category. So basically, it says if you have A0 and A3 balance, now pour in some A2. A0. If I have A0 and A2 balance, now pour in some A3, but subtract the component of A3 that is not normal to A0 and A2. So subtract this component, and this traces out these phase boundaries to almost precisely all the way up to the tricritical point. Up to a small region that in the tricritical point that has some curling here that we haven't understood completely. So let me just say a few words about symmetries. So far, we have given a way to construct critical lattice models and to trace out phase boundaries. But what are the CFTs? What exactly are the properties of the phase transition points that we have constructed? In fact, there is a way to determine the amount of symmetries that is preserved at each phase transition point. And to do that, you have to look into a so-called condensation tree. So a condensation tree basically tells you that for a given topological theory, I can do anyon condensation. Anyon condensation means anyons can escape, right? And the endpoints of condensation give you the gap phases that we just described. And but then you can do the condensation in steps. So I can first condense some of the anyons, and then on top, and then I get a simplified phase. And then on top of this simplified phase, I further condense certain things to reach the gapped phase. And by looking into these intermediate steps, I can trace out a tree, the process of condensation all the way down to the complete topological boundary conditions. And by looking at this tree, so every endpoint here is the Frobenius algebra that I use to compete and to create critical points. In order to obtain the amount of symmetries that is preserved at each critical point, all you need to know is to look at the things that you're competing and look into the tree. Where is there a common parent in the tree? The common parent in the tree determines the amount of symmetries that is preserved at the critical point that we have constructed. So using this way, we were able to basically explain the symmetries in all of these critical points that we found in the model. So finally, I'm already running out of time, but let me say that finally, let's use our method to create new models that people have never seen. And the new model, the new set of models that we are looking into is based on this so-called Haagerup TQFT. So the Haagerup TQFT contains these set of objects. They have these fusion rules. The important thing is it has 7 different Frobenius algebra. We basically computed these things. And then we can draw the condensation tree. And now we can take these Frobenius algebra, compute them, and try to construct phase transition points. And in fact, we find, so let me put a long story short. We basically find a collection of new phase transition points that have not been reported in the literature before. These red numbers are basically the estimated central charge based on numerical calculations. And we also have an estimate of the number of symmetries that these new critical points preserve. And all the value of the critical couplings, the position of the phase boundaries that we find numerically completely matches with the analytic expression that we gave. So it's a beautiful confirmation of the construction. And in principle, you can now construct any number of critical lattice models based on the symmetries that it possesses, described by a fusion tensor category. So let me summarize here. So we have created quite a lot of critical lattice models, but do they have integrability? If they do, much like many of the things that were originally observed, they do have integrability. And so right now we're studying whether our models also possess integrability. If they do, then we would be able to solve them analytically, and so obtain data of the CFT analytically. And more importantly, we're at the point of generalizing these ideas to higher dimensions and hopefully creating more examples of critical lattice models and interacting conformal field theory in discovering new conformal field theories, hopefully also in high dimensions. So let me end here. Thank you very much.